Hello and Namaste. In continuation with the Z transforms, after the detailed introduction about the Z transforms, we are going with the different properties related to the Z transforms. Today's session, we are going ahead with the linearity property and few problems based on this Z transform or the property. Now, what exactly the linearity property? Whatever it's been followed by the other different transforms like Laplace transform or Fourier transforms, we are having a few properties for the Z transforms as well. Out of that, the linearity property says that if f of k and g of k are such that they can be added and a and b are the constants. That means Z transform of a into f of k plus b into g of k is equals to a into z times or Z transform of f of k plus b into Z transform of g of k. The Maclaurin series of the few elementary functions we require it is because this particular Z transform plays very important role in the different areas, and out of that, to find out the answers for the particular questions of the Z transform, we require few of the series, and they are the first one. These are the elementary functions which we require, and they are known as the Maclaurin series. First one is 1 plus z to the power minus 1 is 1 minus z plus z square minus z cube plus z to the power 4 minus z to the power. So if you'll observe here, we have already seen this type of series in the Taylor's and Lorentz expansions as well. So we are going to go ahead with this series provided mod of z is less than 1. Again, if you'll observe, the another series is 1 minus z to the power minus 1 is 1 plus z plus z. So if we have got 1 minus z to the power minus 1, we have got all the positive terms. And if we have got 1 minus z to the power minus 1, then we have got alternate plus minus signs between these terms. But very important thing is to note it down that mod of z is always less than 1 over here. Now, first question is find the Z transform of the function f of k or of the series f of k, where f of k is equals to 5 to the power k is less than 0, and 3 to the power k greater than or equals to 0. Now, if you'll observe here, this is a Z transformation. The definition, we are moving ahead with the basic definition. Definition goes from minus infinity till plus infinity. But this particular function has been divided into two different intervals. It's k less than 0, that means minus infinity to minus 1. It is 5 to the power k, z to the power minus k, plus k is greater than or equals to 0. We have got the function value as 3 to the power k, that is summation of 3 to the power k, z to the power minus k. Summation is from k equals to 0 to infinity. Now, why we have not taken a 0 over here in the first interval? If you'll observe here, we do not have the equality over here. That's the reason it is strict inequality. That means this k equals to minus infinity till it is there for minus 1 only. And then if you'll observe here in the next interval, the equality is involved in this second one. So that's the reason the series or this particular sequence is starting from k equals to 0 till infinity. Now, if you'll observe here, just by putting the values of the k as 1, minus 2 and so on, we'll be getting this value. So if you'll observe here, we are putting the value of k equals to minus 1. So we'll be getting this 5 to the power minus 1, z to the power minus of minus 1, that is z to the power 1. Similarly, k is equals to, so it's equals to k equals to minus 1, k equals to minus 2. This is for k equals to minus 3 and so on till minus infinity this series is. Plus, if you'll observe the second summation, 3 to the power k, z to the power minus k. That is, if we have got, so we have to start with k equals to 0. So if we'll put k equals to 0 in both the things, we'll be getting the value as 1. So this is k equals to 0, k equals to 1, k equals to 2, k equals to 3 and so on. So this is what we are going to get the expansions from the summation. Now, if you observe the first case, now there are different methods to go about and find out the Z transform of the given function. So let us discuss the first one. I will be introducing you with the second one also here in this. So this is k equals to minus 1. So if you observe here, 5 to the power minus 1, z to the power 1 can be written as z by 5. Similarly, this function can be written as z square upon 5 square. Then the next one is can be written as z cube upon 5 to the power 3. So in this way, we can write down this as z by 5 plus z by 5 the whole square plus z by 5 the whole cube, and so on till infinity it will go. Then again, similarly, the other case is also can be written as like, so we have got it here z to the power minus 1. So if you observe here, this is the first term is 1. Second term is z upon 3 upon z minus 1. So if you observe here, 3 upon z to the power minus 1, that is 1 by z. So what would be this? This is nothing but 3 by z. So that is we are going to get it as a 3 by z over here, and therefore we will be going ahead with this type of series everywhere. And because of that, we'll be getting this type of series, and we'll be having this particular series. And if you observe here, this is 1 minus 3 by z. So it is inverse, and we'll be getting this is nothing but mod of z by 5 less than 1. Mod of 3 by z is less than 1, because it's 3 by z because of this particular term. If you observe here, z to the power minus, actually it has to be z to the power plus 1, z to the power plus 2, z to the power plus 3, because it is z to the power minus 1 over minus k over here. So I actually just make the corrections here, z to the power plus 1, z to the power plus 2, and z to the power plus 3 if we are taking it in the denominators. And that's the reason we'll be getting it 3 by z whole square, and so on. And therefore, because of this particular thing, we'll be getting this as nothing but, if you'll observe, this is the series which we are going to use it, because we have got it here, all the terms are all the terms are plus. And in the first case here in this bracket, we'll be taking the z by 5 out, because everywhere in every term we have got z by 5. So if we're taking z by 5 common from this term, let me just move a little back. So if we are taking z by 5 common from the first term, we will be getting 1 plus z by 5 plus z by 5 the whole square, and so on. Similarly, this is the second series, and this is what we are going to use it. 1 minus z to the power minus 1 gives us 1 plus z square, and so on. All of them are positive. That is what we got it here in this. And that means we are going to get it z by 5 into 1 minus z by 5. Check this out. This z by 5. So what is the condition here? The condition has to be getting satisfied, that it has to be mod of z is less than 1. If we are having mod of z is less than 1, that means we have to have it, this condition of this particular thing is mod of z by 5 is less than 1, and mod of 3 by z is less than 1. That means this can be written as, so it's minus 1 raised to minus 1. So it is getting, we are taking it into the denominator. It will gives us 1 minus z by 5 plus 1 upon 1 minus 3 by z. And this is nothing but because of this particular condition over here, this mod of z by 5 less than 1 can be written as mod of z is less than 3. And mod of 3 by z is less than 1 can be written as mod of z is greater than 3. If we'll combine these two conditions, we'll be getting one condition that is known as 3 is less than mod of z is less than 5, which is nothing but is known as ROC, region of convergence, which we have discussed on already. Okay, let me just explain you again with the region of convergence. If you'll observe this type of series, we have taken it in the Lorentz and the Taylor's expansion. Please do follow the playlist from the complex integration over here. Now, if you'll observe here, it's a 0 is the center because it's mod of a z, because that's the reason we'll be having the center of the circle as 0. And the radii are smaller circle with the 3 radius, and the bigger one is 5. And if you'll observe here, 3 is less than mod of z is less than 5 is the region which is shaded over here. This is the region we are talking about. 3 is less than mod of z is less than 5 in this case. This is known as ROC, region of convergence for this particular series. And if we'll just go on solving it, just adjusting, taking the LCM, then multiplying the things, we'll be going ahead with, and we'll simplify this further just by cross multiplication. So if you'll observe here in this case, this 5 will go off from here, and we'll be having this as z upon 5 minus z plus z upon z minus 3. Again, we will this cross multiply, taking the LCM and cross multiplying this, we'll be getting z into z minus 3 plus z into 5 minus z upon this, which is giving us this type of series. And if we'll come, this z square minus z square will go off from here. You will remain here with minus 3z plus 5z, which is minus of 2z upon z square minus 8z plus 15 as the z transform for this particular sequence f of k, which is defined in this way here in this. So this is what we have to solve it, find the z transform of the sequence f of k in this case. Let us go ahead. Okay, that is what this is. Two series are convergent in the annulus. That means the region of convergence is 3 is less than mod of z and mod of z is less than 5. We can combine and can written as this also. Okay. Now the next case is find the z transform of a to the power mod of k. Now again we are defining it, the z transform as it's minus infinity to infinity, a to the power mod of k, z to the power minus k. Then again, if you'll observe here, this a to the power mod of k can be written as in the two intervals from minus infinity to minus 1 as a to the power minus k. And if we have this 0 to infinity, it is just giving me a to the power k. So this is what this particular function can be written as, or can be defined as a to the power minus k in the region k is less than 0, and it is a to the power k if it is k is greater than or equals to 0. That is what we have defined here. So in the previous question that has been given us in the directly 5 to the power k and 3 to the power k along with the intervals. Here it's not given, but yes, we can easily define it, this a to the power mod of k function. Then what we have done it in the last case, the same way we have to do it here. Let me just go one by one. So just by putting the values of k equals to minus 1, minus 2, minus 3. So this is for the minus 1, this is for the minus 2, this is for the minus 3. We'll be getting the series like this. Again putting the same k equals to 0 till infinity. We'll be getting this is for k equals to 0, k equals to 1, k equals to 2, and so on. Just pause the video, try to get this series over here. Again, if we'll rewrite this, we'll be getting something like this here. Again, if you observe az is a common factor from all of them, we can easily take it out. We'll be having the series 1 plus az square, and similarly the other series is 1 plus a by z the whole square, and so on. The one which we have done it last time, the same way, this is the series which we are going to make use of 1 minus z to the power minus 1, and that's the reason it is az into 1 minus az the whole minus 1, and the another one is 1 minus a by z to the power minus 1. This is happening. Then because of this is nothing but can be written as 1 upon 1 minus az, and this is also 1 upon 1 minus az, just by because of this particular series. And this can be written, and we have written from this stage to this one only because we have said that okay, mod of z is less than 1. That means mod of az is less than 1 and mod of a by z is less than 1, and because of that we'll be having this type of series coming out to be the next case, or you can reduce this particular series into this function. And if you just observe here and just go on simplifying further, you will be getting the z transform of the particular function is this, along with this as the ROC. We cannot combine this ROC together because there are the different terms az and a by z. We cannot combine as what we have done it in the last case. 3 is less than mod of z is less than 5. But yes, this can be done as a ROC for this particular z transform. This is a very important task to what we are going to do it as the find the z transform of the unit impulse. Now it's of unit impulse. Delta k is equals to 1 for k is 0, and for it is 0 for k is not equals to 0. Now if we wanted to have the z transform of this particular delta k or f of k, here we'll be writing in this way because of the definition, and we know that delta k, the value of delta k is equals to 1 only for k equals to 0. And that's the reason we'll be having all of them, the values are 0, all the other values are zeros. So if you'll observe here, this is the value 1 at k equals to 0. At k equals to 1, k equals to 2, k equals to 3, and so on. All these values are 0. Similarly, k equals to minus 1. Sorry, just a minute. K equals to minus 1, k equals to minus 2. We are having all the values as 0. That's the reason the z transform of this particular function is nothing but just 1 of this unit impulse function. Very important. Most of the time you might face this is in MCQ type of questions. Find the z transform of the discrete unit step function or discrete unit step uk 0 for k less than 0, and it is 1 for k greater than or equals to 0. Again we are defining it with the z transform, and because of this is uk z to the power minus k from k equals to 0 to infinity, because if you observe here we do not have any value of the function at k less than 0. That means what? the values for 0 less than k is less than minus of infinity, will be getting the value as 0. So this particular value will be having this as 0. Okay, sorry, I've written it cool. Okay, this is minus infinity is less than k is less than 0. We'll have having the value of the function as 0. That's the reason we do not have to even consider. So we are considering here in the second interval. What is the second interval here? Second interval is coming out to be k is greater than or equals to 0. That means k is moving from 0 till infinity. And what are the values? Value is equals to 1. But that means what? This uk is replacing with 1 and z to the power minus k will be always there. So it's 1 plus z to the power minus 1 plus z to the power minus 2 plus z to the power minus 3 and so on. Now, as I've told you, I'll be introducing with the second series or second type of way also. Otherwise, we can easily solve this question using that 1 by z, 1 by z, 1 by z the whole square, 1 by z the whole cube. And the way what we have done is that 1 minus z to the power minus 1 series. What is the another way to deal with this as? We can go ahead and say that this is a geometrical progression series or geometric progression. And if it is a geometric progression, we know what is the sum of this particular series is. Sum is a upon 1 minus r. A is the first term of the series, and r is the common ratio except the first term. So it's a common ratio. Now if you observe this particular series over here, first term is this 1 and the common ratio is 1 by z. Rest of the terms we have got the common ratio as 1 by z, and therefore we can have this as a is 1, and so this is a, and this common ratio is, as I've told you, 1 by z, or you can write down as a z inverse also. So this is nothing but small r, and if you just rewrite this, we are going to get the same thing what we are going to get it from the first two questions what we have discussed with. So it is easy for you all to go about and find out the geometric progression. Sum is always a upon 1 minus r of the series. You can go on solving it, and will be getting this type of examples, or this type of way is also one of the way to go ahead with the Z transform. So few of the questions I'll be dealing with this 1 minus z minus 1 or 1 plus z to the power minus 1 Maclaurin series, or few of the questions I'll be dealing with the geometric progression also. So I'll be using a mixed method for different questions. The reason is only to get acquainted and make you realize that both the methods are giving you the same answer. According to the convenience, we can go ahead and use the methods. Both the methods will give you the same answers at the end. I hope you have understood for this particular thing, and stay connected, stay tuned. Thank you. Happy learning.